Simple harmonic motion. It is called SHM in short and has the following features. It is a to and fro motion and the particle crosses a mean position repeatedly. A varying force acts on the particle continuously. This force is called the restoring force and is always directed towards the mean position. That means when the particle is on the left of the mean position, the direction of force is towards right. And when the particle is on the right of the mean position, the direction of force is towards left. The magnitude of this force is directly proportional to the displacement of the particle from the mean position, which is x. The negative sign indicates that the force and the displacement are oppositely directed. Now force is equal to mass times acceleration, where acceleration is equal to second derivative of displacement x with respect to time. Let the proportionality constant be k. Then this is the time displacement differential equation for SHM, which is to be solved. We multiply the equation by dx dt. We can also write this as dv dt and dx dt as v. Now we multiply by dt and integrate to get this relation where c is the integration constant. Now at maximum displacement, which is called amplitude of SHM and is denoted by a, the particle changes direction and the velocity is 0. Putting x equal to a and v equal to 0, we get c equal to ka square. So we get this equation. Now we write dx dt for v and get another differential equation. This is easily solved and this is the solution. Here integration constant is phi. This is called epoch. Now what is epoch? It is not necessary that we start SHM from the mean position, that is x equal to 0 when t equal to 0. However, if we start the SHM from mean position, then epoch phi equal to 0. If we start the SHM from a position other than the mean position, then the epoch phi has these values. Now a student may get confused by seeing these angles in the time displacement equation of SHM. Where do these angles come from? For this purpose, you need to know the concept of reference circle in SHM. Consider a particle moving along a circular path with a radius equal to a, the amplitude of SHM at uniform speed like this. Now let's join the two particles. What do you see? The displacement of both the particles is same all the time. So this particle will also have the same time displacement equation as this for SHM. To verify, we'll stop the animation and the displacement is calculated trigonometrically. Now this theta by t is the angular velocity in radians per second, denoted by omega. Comparing with this equation, we get k by m equal to omega square. Here k is called the spring factor and m is called the inertia factor. Velocity time equation of SHM. This equation is a cosine function. Velocity is 0 when omega t plus phi equal to plus minus pi by 2, that is displacement equal to plus minus a, and velocity is maximum when omega t plus phi equal to 0 where x equal to 0 and the maximum velocity is equal to a omega. Acceleration time equation in SHM. Compare it with the time displacement equation. They have 0 values at the mean position. Displacement and acceleration are opposite in direction, which is the real essence of SHM. Energy of particle executing SHM. Total energy is the sum of kinetic energy and potential energy. Let's calculate kinetic energy. It is equal to half m omega square a square minus x square. Kinetic energy is maximum when x equal to 0, that is at mean position, and 0 when x equal to plus minus a. Let's calculate potential energy. Let position of particle be at C where displacement OC equal to x. Work done to move a small distance dx at that instant is equal to force times displacement. So what is the total potential energy gained at point C starting from mean position? We have to add all the small work done from mean position to position C. We assume that potential energy is zero at mean position. Potential energy at point C is got by integrating this equation within limits 0 to x, and we get potential energy is equal to half m omega square x square. Potential energy is maximum at x equal to plus minus a and 0 at x equal to 0. We see that total energy is constant throughout.